So from last time, the estimator for beta 1 hat stat, the estimator for beta naught is beta naught hat y bar minus beta 1 hat times x bar. In practice, you start with beta 1 hat, estimate at first, and then we move on to beta naught hat. This part is fine, the expression for beta naught hat. The expression for beta 1 hat looks a bit messy. So we can actually simplify that and write it in a different way. So we will start with SXX. SXX, based on all the notation that we've done, if you have to take a guess, what would that be? So if you look at SXX, it's not the standard deviation, rather it's just the variance. Variance is expressed in terms of some of its squares. There should be a factor here of 1 over n minus 1. If you go back to statistics 2023 and look at the formula for variance, S squared would be 1 over n minus 1, I equals 1 to n, xi minus x bar squared. Yes. Now we sort of denote the sum of squares as just x in the textbook because that's why I would make it confusing. But do keep in mind, even though I call it x, it is variance of some sort. That's 1 over n minus 1. I'm ignoring it because when I get back here, it has to be 1 over n minus 1 in the denominator, 1 over n minus 1 in the numerator. They will get cancelled. So I'm just ignoring that 1 over n minus 1. So by all means, the sum of squares is related to the variance, ignoring the factor 1 over n minus 1, which will get cancelled. So variability in x. Another way to recognize this is x varying with x itself. So xx. So we get this and thus are one and the same because I can rewrite this. What should you do here? Where would you start if I want to rewrite? Expand. So how would you expand for? What? Can't hear you. Did you have breakfast? So we're going to FOIL. So if you FOIL, you get xi squared minus 2 xi x bar minus x bar squared. Distribute the sum. The first term, sum equals 1 to xi squared. Second, 2 x bar xi. The third term, good so far. There's nothing I could do the first term because the index I is there, so I'm just going to leave it as is. The second term, what is constant or what are constants in the second term? 2 x bar is a constant, so I can pull that out. I just mentioned that x bar is a constant. If x bar is a constant, x bar squared is a constant. If you sum n constants, what do you get? N times x bar squared. I believe I wrote this last time, but I'll write it again. These are side notes, so put it in the side. Don't confuse with this part. If you want to find the sample mean, you sum all the x values, divide by f. If you rewrite, we can write sum I equals 1 to n xi. That's n times x bar. We did this last time. Good so far. Going to replace that sum as n times x bar. Good. Which would result in sum I equals 1 to n xi squared minus 2 n x bar squared plus n x bar squared. What would that reduce to? So I have 2 of these n x bar squared, and when it's that, if you simplify, those two will cancel. Result in simplify this is going to result in that. So write the denominator as sx, which is the same as, say, that would equal to n minus 1 times s(x), which is the sample variance of x over here. Do we agree? Yes, no, maybe. Good. You may ask me, well, why is he writing it that way or writing it this way so that we can use it easily when we do an example? Because the calculator is going to provide us with the variance. Good. We'll move to the numerator. Going to go to sidebar again. I want to retain this. I'm going to ask a question. So I wrote it as sxx. Now I said that there's the sum of squares in or for the x values, which is related to the variance. When we started the derivation, I rewrote this. I wrote it as 1 to n xi minus x bar, xi minus x bar. Good so far. We did that already. That's where I started. Good. With me. here's the question. If that's the case, logically, I'm not asking you to give me the correct answer, but think about logic and tell me what SXY would look like. It is sexy. So I wrote it as SXX because that part is X, that part is X. If I use the same logic, that will be sum I equals 1 to n. Xi minus x bar, yi minus y bar. Good. Well, use the same process. Xi yi minus xi yr minus x bar yi plus x bar y bar. Agreed? Okay, so most of you got it. So distribute the sum. Minus 1 to n xi y bar minus sum 1 to n x bar yi plus sum I equals 1 to n x bar y bar. That's done. Can't do anything about it. Leave it as is. The second term, y bar, is a constant. Third term, x bar, is a constant. Last term, x bar, y bar, both are constants. If you multiply, you get a constant. Sum n times, so n times x bar, y bar. So first will remain as is. Second term, I can write it as y bar times n x bar, same logic. Third term, x bar times n y bar, same logic. Last one, n x bar y bar. Yes. Get rid of those two terms. If you look at the results, that is xi yi minus y bar n times x bar y bar. It's the numerator. Good. So I can rewrite the numerator as x. Good. Again, why we're doing this? Because we want to use the calculator. And so erase this part. Now, you probably don't know covariance. Evan knows all about it, and I'm sure Nick Dennis does too. Why am I rewriting in terms of covariance? Because I'm going to put correlation. You know about autocorrelation also. And and that formula will get simplified. So I'll call it C. C stands for covariance. What does co mean? Co means together. So there are two things. For the sample, the covariance is 1 over n minus 1 xi minus x bar times yi minus y bar. Good. If I rewrite that, I showed earlier that equals the derivation we just did, sxy, so that part is sx1. If I rewrite that, sxy would be n minus 1 times c, the covariance. Good? What are you so happy about?
It's not happy. It's not hard.
Good. Going to take this and put it in there. N minus 1 times c. What happens to the n minus 1? It will get cancelled. So that'll go away, that'll go away. It simply has c over s x y. So R is the linear correlation coefficient, and it's also sample correlation. In short, but the formal name would be linear correlation coefficient. Great. R is simply C, the covariance divided by Sx times Sy. Earlier mentioned Sx squared is the variance of x. If Sx squared is the variance of x, what is the square root of Sx squared? The square root of variance.
Standard deviation.
Standard deviation. So this could take the square root of variance, you will get the standard deviation. Naturally, Sy will be standard deviation. The formula, I won't get into it by additional derivation, but from a logical standpoint, it is looking at the proportion of two things varying relative to how they vary individually. Yes? So that will measure the strength of correlation, just the logical force. There is a derivation for that. So using that, I can rewrite C or times Sx times Sy. Do we agree? Going back here, I'm replacing C by whatever I have here. I skip the derivation of that part. Now, how would that simplify? Very good. So that'll get cancelled. Simply have R times SY divided by SS. So we did all that to demonstrate how this, the constant, you can either use sum of squares to compute beta 1, or you can use covariance and variance of x to find beta 1 hat, or you can use standard deviation of y, standard deviation of x, and the correlation coefficient to find beta 1 hat. Once we find that, we go back here, plug in beta 1 hat, sample mean, we know how to get for x, sample mean, x can be for y, sample mean for x, and you will solve for beta 1 hat. Good? So far? Okay. And finding these, relatively easy using your calculator, we're going to get into that. Okay, time for example.